the name of Almighty God, I am Hafsa Sankoshi, and today I want to talk about the next chapter of Physics GRE, which is circular motion. One kinematic situation that arises often on GRE question is circular motion. We will consider this in a slightly more detail in section 1.3, 1.6 when we discuss orbits. For now, consider a particle moving on a circular path. Its acceleration vector can always be decomposed into radial and tangential components. If its tangential acceleration is zero, then its tangential velocity is constant. It is moving in uniform circular motion about the center of the circle. But its radial acceleration is non-zero and has value as acceleration is equal to v to the power of 2 divided by r, where v is the speed of the particle and r is the radius of its orbit. From this, we can immediately also infer that the force needed to keep the particle on in its orbit, the centripetal force, is F is equal to m point v to the power of 2 divided by r. Indeed, since the tangential acceleration is zero, it must experience some force directed radially inwards that keeps it moving in a circular path at a constant speed. Remember that this doesn't tell you what kind of force is acting on the body. It just tells you that if you see a body moving uniformly in a circular or radius r with constant speed v, then you can determine what centripetal force must be acting on it. While uniform circular motion is perhaps the most common example, it is certainly not the most general. There are many cases of non-uniform circular motion. For example, a roller coaster going around a circular loop-the-loop, or a vertical pendulum attached to the rigid rod with sufficient initial speed to complete a full revolution. In these cases, the angle between the gravitational force vector and the velocity vector varies as the object goes around the circle, giving a varying tangential acceleration in addition to the centripetal force, and the above formulas don't apply throughout the whole orbit. However, the uniform circular motion equations do apply at two very special places, the top and bottom of the circle, where the gravity acts purely vertically and thus radially, such that the object is instantaneously in uniform circular motion at all other points in the orbit. Other methods, such as energy conservation, must be used to find the velocity. The centripetal force equation is not so interesting on its own, so a very common class of problems involves combining it with some other type of physics. A typical template might look roughly like this. A particle is moving in a circle. Identify the physics that is causing the centripetal force. Set the expression for this force equal to the centripetal force. Then solve for whatever quantity is requested. Section 1.2.2 Problems Kinematics. Here there are two different questions, and then we reach to the next example. An electron charge it moves perpendicularly to a uniform magnetic field of magnitude beta. If the kinetic energy of the particle doubles, by how much must the magnetic field change for the particle's trajectory to remain unchanged? We know that the magnetic force on the electron is perpendicular to its motion. See the section 2.2.6 for a review. So it is a centripetal force and the electron moves in circle. More specifically, the forces are constant, so the electron executes uniform circular motion. Setting the magnetic and centripetal forces equal gives us electron volts beta is equal to m point v to the power of 2 divided by r. Rearranging just a little, we can find the magnetic field as B or beta is equal to m point v divided by er. If the kinetic energy of the particle doubles, its velocity increases by square 2, so b must increase to square 2b in order to maintain the same radius. This template occurs very frequently through circular motion, can involve many different types of physics, identifying the centripetal force and setting it equals to m point v to the power of 2 divided by r will give you an additional equation to help solve the problem at hand. Section 1.3 Energy. Conservation of energy can be stated as follows. If an object is acted on only by conservative forces, the sum of its kinetic and potential energies is constant along the object's path. Conservative forces are those for which the work done by the force is independent of the path taken between the starting and ending points. But the most useful definition, although it seems tautological, is a force to which you can associate a time-independent potential energy. The most common examples as gravity, spring forces, and electric forces. The most common example of a force that is not conservative, and probably the only such example you will see on the GRE, is friction. An object traveling from the point A to the P and back to a wheel slow down due to the friction the whole way through, even though the starting point is the same as the ending point. A standard subset of GRE classical mechanics problems are most easily solved by a straightforward application of conservation of energy. It's important to recognize this problem so you immediately jump to the fastest solution method rather than fish around for the right kinematics formulas, so we will set a general principle. If you want to know how fast or how far something goes, use conservation of energy. If you want to know how much time something takes, use kinematics. It's baffling that this simple dichotomy isn't introduced in first year physics course. It's based on the idea that total energy is a combination of kinetic energies which depend on the velocities and potential energies which depend on the positions. Setting E or energy initial is equal to energy final. Let's use solve for one in terms of the other, but nowhere in the equation does time appear explicitly. On the other hand, kinematics gives you explicit formulas for position and velocity as a function of time to see equation 1.5. Of course, some problems will require a combination of both methods. For example, using conservation of energy to solve for a velocity, which you can then plug into a kinematics formula. But as a very general rule, if time doesn't appear in the problem, then you can leave kinematics out of the picture. However, we will address a common exception to this rule at the end of the section 1.3.2. Chapter of 1.3.1.1 Types of energy. To begin with, you should know the following formulas. Code 1.5 is translational kinetic energy 1 divided by 2 m v to the power of 2. Rotational kinetic energy 1 divided by 2 I omega to the power of 2. Gravitational potential energy on Earth mgh. Spring potential energy 1 divided by 2 k x to the power of 2. Hopefully the standard notation is familiar to you. V is the linear velocity, omega is the angular velocity, m is the mass, I is the moment of inertia, h and x are displacement. G is the gravitational acceleration at Earth's surface, which should always be approximated to 10 meter per square second. And the GRA when numerical computations are required and coils spring constant. There are two important points to remember about the potential energy. The first is that it is only defined up to an additive constant. We are free to choose the zero of potential energy wherever is most convenient, which is usually some physically relevant positions such as the bottom of a ramp or uncompressed length of a spring. It is measured from the central mass of an extended object. The usefulness of the center of mass concept, see the section of 1.4 is that it allows us to treat extended objects like point masses, with all their mass concentrated at the location of the center of mass. There are other types of potential energy, but all can be summarized by definition. For any conservative force F, the change in the potential energy delta U between points A and B is delta U is equal to minus the integral with the lower bound is A and upper bound is B. F differential I. The line integral looks scary, but it really isn't, since in all cases of interest, the integral will be along the direction of the vector. Force vector. Probably the only time you might have to use the formula is if you cannot remember the electrostatic or gravitational potential right away. So we will do that example here. The gravitational force between two masses m1 and m2 is F gravitational is equal to g m1 m2 divided by r to the power of 2 r. You may have seen this equation in the form of F gravitational 1 on 2 is equal to minus g m1 m2 divided by r to the power of 2 and r, Preen stating that the force on mass m2 from m1 points along the vector r from m1 to m2 with a minus sign to indicate that the force is attractive. As we will see, there are minus signs everywhere, so even though it's deliberately a bit ambiguous, so we find 1.10 a more useful mnemonic conceptual for the GRE. Just remember that the gravity is attractive and fill in the sign depending on which force 1 on 2 or 2 on 1 you are computing. See example 1.5. Alternatively, if you are given the potential, you can compute the force by inverting equation 1.9, and the equation in 1.11 is F is equal to minus U. Again, watch the minus sign. So thank you so much for watching my tutorial video until the end. Today is 23rd of March 2026. Time is 11:34 p.m.